surface up here, we'll call this one surface A2. Now, of course, A1 is radiating to A2, and A2 is radiating to A1. They're exchanging energy. So now we have Q1-2. That's the net heat transfer from 1 to 2 between A1 and A2. Okay, and that's equal to A1J, let's put it down, A1J1F12 minus A2F12J2. The first term is what's leaving surface 1 that's getting to surface 2 minus what's leaving surface 2 that gets to surface 1. That's the net heat transfer between those two surfaces. But then we recall reciprocity. So in that case, A1F12 equal A2F21. So then we can get rid of A2F21. So now we have A1F12 J1 minus J2. Rewrite it. And we get Q12 J1 minus J2 divided by 1 over A1 F12. Q12 is the net exchange of thermal radiation between the two surfaces A1 and A2. Yeah.
Are we assuming that all radiation goes between the two surfaces and there's nothing?
Yeah, that's just between those two.
Okay.
Not the room walls. There's A1, there's A2. There they are, right there. How much radiation is between A1 and A2? That's not the room. No. That's later. We'll do that later. But for right now, it's just these two surfaces. Somebody said, you know what? That looks like Ohm's law. Here we go again, you know. Left-hand side is an energy flow, not a current flow, I. The right-hand side numerator is something that drives the process. It's not a difference in voltage. It's a difference in something called radiosities, J1 and J2. So the thing in the denominator can be interpreted to be a resistance. So we call that resistance 1 over A1 F12. And that is, units are again the same thing, of course. Units, meter to minus 2. It's called a space resistance. Not because it's in outer space. It's because its value depends on the space between the two objects. Its value depends on the view factor, and the view factor depends on how one surface sees another surface. Its geometry, its orientation, how far apart they are. So it's called the space resistance. It's a function of how far they're spaced apart. That's what it means, space resistance. So every pair of surfaces in an enclosure has a space resistance. If F12 is small, that resistance is big. If F12 is big, then that resistance is small. If you want to do it graphically, here's the resistance. Here's J1. Here's J2. 1 over A1 F12. And this is going to be Q12. Q12. So there's how it looks. So, you know, there's A1. So I'll put A1 right there. And there's A2, okay. So if I want to find F12, oh wow, it's got to be less than a couple percent or less, because the radiation leaving A1, very little of it's going to get to here. Most of it's going to go to the ceiling, the floor, the back wall, the front wall. So the view factor might be 0.05. Yeah, okay, now it's 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.99, because area A1 almost sees all of area A2. The view factor is close to 1. Get them within 1/10,000th of an inch. View factor 0.999. Yeah, it depends how close they are. And why is it view factor? Well, it's what I see. In my field of vision right now, that's probably 20% of my field of vision. That's probably 0.5 right there. And that's close to 1. That's why it's called a view factor, because our eyes give you some intuitive feel for these F values. Okay, so now we've got all we need to look at an enclosure. And we'll take, first of all, the simplest enclosure, which is a two-surface enclosure. Let's see, I think I'll start over here. A two-surface enclosure. And all this stuff leads up to your next numerical problem, which is going to be using numerical methods to solve these algebraic equations. So two-surface enclosure. I'm going to go back to our simple one of about a week or 10 days ago, where we had a circular base and above it was a hemisphere. And this is going to be called surface A1, and the hemisphere A2, and we always look at the inside because that makes the enclosure. The enclosure is inside. Now, if we want, we can, let's just say, for argument's sake, let's say that for area A1 we have T1 epsilon 1. For area 2 we have T2 epsilon 2. And let's just say, for argument's sake, that T1 is hotter than T1, so we can talk about which way heat flows. Okay, here's the rule. Every surface in the enclosure has a surface resistance. Every pair of surfaces in the enclosure has a space resistance. How many surfaces? 2. How many surface resistances? 2. How many space resistances? 1. Okay, 3 resistances. You start out here and say, okay, I'm going to call that right there, epsilon, EB1. EB1. There's a resistor there connecting to what? What leaves the surface? J1. What is that resistance? 1 minus epsilon 1 over epsilon 1, A1. Okay, good. Now, surface 1 connects with surface 2. How? By a space resistance. This connects the surfaces. What's its value? Well, right down here. There's J1. There's J2. Okay. J1, J2. What's that resistance? 1 over A1, F12. What's the heat flow here? Q1. What's the heat flow here? Q1-2. Now we're at J2. Go back to here again. J2 connects with the surface EB2. Surface is EB2. 1 minus epsilon 2, A2, Q2. So I say, you know what? This two-surface enclosure, this is in series. Okay, right, this is a series connection. If it's in series, here's how I find the heat flow Q. And by the way, since it's in series, I know that Q1 equal Q2 equal Q1 dash 2. So Q1 equal Q1 dash 2 equal Q2. Okay, that's equal to, now don't forget heat flows left to right because we're assuming that this is hotter, T1 than T2. What's EB1? Sigma T1 to the fourth. What's EB2? Sigma T2 to the fourth. We normally know those two guys. Normally, the temperatures are given to us. So normally, we know EB1, we know EB2, we don't know J1, we don't know J2, we do know resistance R1, we know R12, we know R2, but we don't know the Qs. So what can you find here? You can find, by this analysis, J1, J2, and any Q you want. They're all the same. We're going to find Q, though. Most heat transfer analysis, you want to find Q. Okay, on the top, the big number, EB1, minus the smaller number, EB2. Why? Because I know both of those guys. If you know them, put them in there like that. Divided by the sum of the resistances. 1 minus epsilon 1, A1, 1 over A1, F12. 1 minus epsilon 2 over epsilon 2, A2. There it is for that picture up there. That enclosure, hemispherical enclosure, surfaces A1 and A2. Oh, it'll work for any two-surface enclosure. We also talked about this one. We have a sphere, A1, a baseball inside of a basketball, A2. Yep, there's the equation right there. Same thing, right there. Any two-surface enclosure that works for. Okay, now, let's make life a little easier. Let's say if surfaces are black. R1 equals 0, R2 equals 0. And we call these guys right here, we call this one R1, R12, R2. Okay, EB1, EB2, Q12, R12. So Q12, sigma T1 to the fourth minus T2 to the fourth divided by R12. In the first picture up here, A1 pi d squared divided by 4. F12, 1. This picture right here, area 1, pi d squared, pi d1 squared. F12, 1. Okay, simple to get, you got it. Okay, let's take another one. This one is going to be, I'll take that same equation here, but now I'm going to say that I'll just copy it down again. Okay, Q1-2. And I'll put it in there in terms of temperatures since we know the temperatures normally. Sigma T1 to the fourth, T2 to the fourth, divided by Okay. Now, this one up here, of course. This is for black surfaces. This one's going to be for small surface in a large enclosure. They're not black. And of course, in these guys over here, F12 was 1. For this guy here, of course, the same pictures over there. F12 is 1 from my pictures over here. Okay, so now I'm going to rewrite this. I'm going to multiply this last guy over here by A1 over A1. I didn't change anything. Now I notice that there's an A1 in every term in the denominator. A1, A1, A1. Pull it outside. Flip it upstairs. A1. Okay, 1 over epsilon 1 minus epsilon 1 over epsilon 1. 1 over F12. F12 is 1. 1 over 1 is 1. Plus this term right here. Pull out that A1. Okay. Minus 1 plus 1. Okay. Now here comes the assumption. Someone's told me in the problem, I've got a small surface in a room, that's this one, or they say to me, I've got a surface in a large enclosure, that's this one. It can be stated either way in a problem, but they both give you the same conclusion. A small surface, that means A1 is small compared to A2. A large enclosure, that means A2 is much larger than A1. Conclusion, if they're much, much larger, the ratio A1 over A2 goes to 0. Goodbye. Q12, epsilon 1, A1, sigma, T1 to the 4th, T2 to the 4th. Yeah, that's the equation we had way back in chapter 1. In chapter 1, we said to handle radiation exchange between two surfaces, if it's a small surface in a large enclosure, you're allowed to use equation 7.1. And we said, don't ask me why right now. Wait about 4 weeks. Well, now it's the 5th week, 6th week. So now we know why. This is the proof for the equation in chapter 1, equation 1.7. It holds for what? Well, of course, two surfaces. And here it is. F12 is 1, small surface in a large room. Put a dime on the floor here. Take all the chairs out and the desks and things out. Put a dime on the floor. That's surface. That's a small surface. The room walls, the area comparison, add those 5 room walls in here. Compared to a dime's area, it's negligible. That term would go to 0 for sure. Small surface in a large room. Okay. All right, good stop.